Good evening and welcome to the Ann Arbor District Library on AADL TV. Thanks for tuning in for tonight's presentation of Exploring the Mind with the University of Michigan Department of Psychology. In just a moment, Christopher Monk will introduce our guest, Dr. Julie Bolin. To find past Exploring the Mind programs or view other virtual events, visit aadl.tv.
Thank you very much for joining us. Today, it is my pleasure to introduce Dr. Julie Bolin. Dr. Boland is a professor of psychology and linguistics here at the University of Michigan. She completed her undergraduate degree at Washington University in St. Louis, where she graduated magna cum laude, and she went on to get her PhD at the University of Rochester in the Psychology, Language, and Cognition program. Dr. Boland has been a professor at Ohio State, Rutgers, and the University of Louisiana, and she joined the faculty here at Michigan in 2001. She has received many awards and grants. I want to just highlight two that I think are particularly notable. First, she recently won the University of Michigan Provost Teaching Innovation Prize for developing new ways to make the teaching of research methods more effective and inclusive. Second, she received a grant from the Association for Psychological Science to promote anti-racism teaching. Dr. Boland's research brings together fundamental questions about cognition and language. Questions she asks include, what is the relationship between the structure of a sentence and our comprehension of that sentence? How do we resolve ambiguities in language? And finally, how is grammatical knowledge represented for people who speak multiple languages? Today, though, she'll be talking about a new line of research. Specifically, she'll be focusing on Zoom, a product that many of us have become very familiar with in the last 2 years. Dr. Boland's talk is entitled, Zoom Disrupts the Rhythm of Conversation. Here is Dr. Julie Bolin.
Thank you, Chris, for that nice introduction. And thanks to the Ann Arbor District Library for giving me this opportunity to share some of my research. Like Chris said, this is fairly new research. I'm a cognitive psychologist and I do research on language processing, and most of my research is focused on language comprehension, which is kind of surprisingly complex. So when you're listening to me now, you're hearing a fairly continuous stream of vocal sounds, and you have to segment those into recognizable words and then organize that sequential string of words into a hierarchical grammatical structure and interpret the words in that structure as the message that I'm trying to convey. And hopefully you will be successful in that. And as we do this, we're faced with lots of ambiguities about where one word ends and another begins, about what a word means in this particular context, or how the words are structured to form the sentence. Likewise, on the production side, if you are formulating an utterance that you're actually going to produce, that's also a complex task. You have to decide what message you want to convey. You have to choose your words and the grammatical structure you're going to use, and then you have to organize the words and the little constituent parts of those words, the phonemes, into the correct order, and then prepare an articulatory plan so that you perform the right movements in the right order. So given the complexity of comprehension and production, I have always been a little bit wary about investigating conversation because it seems like a lot going on at once. You've got, the same person switching back and forth between the role of comprehension and production. But I became intrigued by a particular puzzle. And that is, it seems obvious that you can't completely formulate your response until the person you're talking to has finished what they're saying, so you can respond to that. But yet the turn transitions, the time between speakers, are really short. And I mean really short. So we can measure the transition time as the difference between when one speaker stops and the other speaker starts talking. And if there's overlap, that'll be a negative number. If there's a little gap, that will be a positive number. And you can see this histogram that is summarizing all of the turn transitions in 2,400 phone conversations between strangers that happened in 1990. I was a graduate student at this time, and I remember seeing ads to call this number to contribute to this database. And people called more than once. You get like a robot that assigns you to another caller as your conversation partner, and they give you a topic, and you guys talk about that for as long as you want, and then you hang up. And so it's not really an optimal sort of situation. It's over the phone, you're not talking to a friend, but even so, most of the turn transitions the times kind of gathered around 0. And virtually all of them go between -1 second and +1 second. So these numbers are in milliseconds, so 1,000 milliseconds equals 1 second. And this very tallest bar here represents all the turn transitions which happened between 100 and 200 milliseconds, a silent gap of just 100 to 200 milliseconds. Now that's really fast. And even doing something like moving your foot from the accelerator to the brake when you're driving takes about half of a second, just to put that into some perspective. Now you may think, well, it's going to vary a lot across languages, and a group led by Stivers did look at 10 different languages from a lot of different language families, and it does vary across languages, but in all of the languages, the average turn transition time was under half of a second. And you can see English here in the middle with an average turn transition time of 236 seconds. Now, to put some context around 236 seconds, let me give you a really simple task. I'm going to put a picture up on the screen, and I want you to name that picture as fast as you can. Just say what it's a picture of with a single word. Okay, apple, right? Probably you said apple. And people have measured the time it takes people to do this task, and it takes about 600 milliseconds just to say a single word. So how is it that within 100 or 200 milliseconds, we can formulate a complete sentence and respond to our conversational partner during conversation? Well, what this means is that we must not be waiting until the end of our partner's utterance to begin planning our response. The listener has to be doing at least 3 things simultaneously. First, they have to be comprehending the speaker. And as I said, that's already a complex task. They have to be deciding on their response and planning it to the point where they're ready to at least begin speaking. And then thirdly, they have to make a fairly accurate prediction about when the speaker will stop talking so that they're ready to go and execute their response at the appropriate time. So this made me wonder if conversation is actually sort of this difficult multitasking operation that requires your full attention and could fall apart like any time, like a one-man band, you know, that seems like really hard and complex. If that's the way conversation is, it should be very demanding of something called cognitive control, which includes the ability to switch quickly between tasks, to ignore irrelevant information, and regulate your attention to achieve your goals. These cognitive control capacities decline as we age, but as far as we can tell, elderly people who have lower cognitive control abilities don't have any longer or more variable transition times than younger adults. And furthermore, our own intuition suggests that conversation is actually kind of easy, and sometimes we can do other things while we're conversing, like driving a car or looking at something, searching for something on our phone. So just our intuitions tell us that conversation isn't actually all that demanding, yet we're doing at least 3 complex things at once. So some of that must be happening pretty automatically. We investigated this, this idea that conversation doesn't completely exhaust all of our cognitive capacity by bringing people into our lab. This was pre-pandemic, and having them converse with an experimenter while they were carrying out a secondary task that varied in difficulty. And I thought that, you know, when we gave them the harder versions of the task, the conversation would really break down, but it didn't at all. We did find measurable differences in the transition times, but they were on the order of 100 milliseconds and still within a normal range. So when we took those conversations and we made clips of them, little short audio clips, and played them for a different group of participants that we brought in, the participants couldn't categorize the conversations as either belonging to a condition where there was no secondary load at all and people were just talking versus where there was a challenging secondary task. So transition times are really robust against multitasking, and multitasking beyond just the multitasking that's involved in conversation itself. And it suggests that we must be able to time the onset of our turns pretty automatically without requiring a lot of conscious attention and planning. So some researchers have suggested that dancing is actually a good metaphor for a conversation. So when we dance in sync with a partner, we can anticipate our partner's moves and coordinate our own moves with them pretty precisely. Let's continue thinking about music. Even if you're listening to music alone, we have a way of tracking the beat of the music. And this beat tracking can be instantiated as an automatic neural oscillatory system. So an oscillator is a group of neurons that are firing in a rhythm to some stimulus. It can be an external stimulus or it can be an internal stimulus, you know, like hunger or sleep-wake cycles. An oscillator could be a good model for how we perform rhythmic activities. And a pair of ballroom dancers could keep in synchrony in part because their internal oscillators are synchronized to the same music. So this allows them to not only move together with their partner, but also to predict the timing of future actions by their partner and by themselves. So could an automatic neural oscillator help us time our responses during conversation? Researchers have been interested for a while in looking at this idea of neural oscillators tracking speech, though not in conversation, in this more sort of contrived situation. So this, this slide shows you some research by Ding and colleagues who found evidence that automatic neural oscillators track syllable rates. What they did was they put scalp electrodes on people while they listened to words that were presented. They were one-syllable words, and they were presented every 250 milliseconds. So 4 words a second, or we could say that as a frequency of 4 hertz. So what they found in the electrical, in the record of electrical brain activity was this peak at 4 hertz, representing the rate at which these syllables had been presented. And furthermore, there was evidence of higher level linguistic structure. These one-syllable words also formed noun phrases and verb phrases, and then the noun phrase and the verb phrase formed a sentence. And there was evidence of that higher level linguistic structure also. So it appears that these neural oscillators automatically track both syllable rate and higher levels of linguistic structure, at least when the words are presented in this really metronymic kind of fashion, where a really rigid rhythm. Now we know that language isn't really like that. People don't talk to a metronome, and music isn't even like that. There's some variability in the rhythms of music also. So it remains kind of an open question how much variability an oscillator could tolerate before it was no longer able to track the rhythm of speech. But assuming that an oscillator could track our somewhat fuzzy rhythms of speech, it provides an automatic mechanism that could help us time the initiation of our responses. So let's look at, this is a spectrogram of a sentence that was said by one of my undergraduate experimenters. It was a stimuli for the one piece of stimuli for the first experiment that I'm going to tell you about. And she's saying, do you think that surfers are scared of being bitten by a shark? And it's said in just a perfectly natural way, not to a metronome or anything like that. Then I used an algorithm to automatically find the syllables based on the acoustics of the speech. And those syllables are numbered 1 through 15 by that algorithm. They're marked on the slide, these blue numbers here. You can see that some of the syllables are quite short and some are quite long. They're not all the same length, but that isn't necessarily a problem for the oscillator if the duration of the longer syllables is a multiple of the duration of the short syllables. So let me kind of illustrate that a bit better. But if I overlay an oscillator that has a period that's pretty consistent with that of the shorter syllables. And what I want you to notice is that most of the syllables fall near the sort of lowest point of the oscillatory cycle. That means that it's an opportunity, or a sort of timing opportunity when you could begin speaking. Now, of course, you need more than just that oscillatory information. You need to know where the other speaker is in their sentence. But the oscillator could be combined with some pretty strong cues from intonation, for example, that would tell the listener how close the speaker is to the end of the sentence. So the oscillators couldn't provide everything we need, but could provide something important in a very automatic, effortless way, sort of subcognitive. Now, based on research on music processing, where there's been much more work on oscillatory theories than in speech processing, it's been hypothesized, or there's evidence that an oscillator can remain synchronized with a fuzzy rhythm as long as the deviations are less than 20% of the period. So using this sentence as our example, the period of the oscillatory cycle is about 100 milliseconds. So a 20% error tolerance would be about 20 milliseconds. Now, so that amount of error tolerance, I think, is enough to handle the fuzzy rhythms of this particular sentence that we're looking at. Where the syllable doesn't exactly hit the bottom point of the cycle, it's still pretty close and it's within that. But on the other hand, because speech is quite variable and maybe even more variable than is illustrated by this one sentence, the natural variation in speech rhythms might already be close to maximizing the tolerance of a neural oscillatory system. So this brings us to Zoom fatigue and the role of Zoom when we're talking to each other in this remote manner, right? So in any kind of electronically transmitted communication, but especially in Zoom, where we have both a video image, and an audio data, the voice and the image data get assembled into packets. They get sent across the internet and then reassembled at the other end. If you have a really poor connection, you might actually miss some packets, and you might notice a little bit of jitter in either the audio or the video. But even under optimal circumstances, there will be some lag, some electronic transmission delay or latency that is variable and depends on things like the current traffic on the internet and some other factors. And so the question we had was whether or not this additional transmission leg would be add too much variability to for our oscillator to stay in sync with the rhythm of speech. And remember, if the oscillatory period is only 100 milliseconds, then it can only tolerate about 20 milliseconds of error, and there's already some error in the speech. So if the oscillator gets disrupted, our hypothesis was that it should take more effort to time our responses, and also should lead to longer transition times and a more kind of effortful conversation experience. So it might be one component of the Zoom fatigue that people talk about. So I want to tell you about 3 different experiments, and there's going to be a bonus experiment also, where we use 3 different paradigms to try and investigate this question. In each paradigm, there was a local condition where there was no Zoom involved, and then there was a remote condition where the conversation happened over Zoom. And the different paradigms vary in terms of both how naturalistic they are and how much experimental control there is. And as you might guess, the more experimental control, the less naturalistic they are. So the idea is to kind of look at this from 3 different directions and see if the 3 experiments converge on the same answer. So in our first experiment, we had a very carefully controlled question and answer paradigm. All participants heard exactly the same questions, and they were pre-recorded. So they heard exactly the same question in exactly the same way, same rhythm and all that. And the answer was always just a simple yes or no. So we're controlling the duration of the question, all the details about the question, and we're also controlling a lot about the response, that it's just a single word, yes or no. What we did was we recorded all of our questions, and then we put them into a PowerPoint slideshow, or I think it was actually Google Slides, with 1 question per slide, and the audio file played automatically when a new slide came up. Participants would listen to the question and say yes or no as quickly as possible. And it's, you know, an artificial task. It's not very much like conversation, but we told them that we were interested in conversation, and we wanted them to, you know, act as if this was a live person, and just to respond as quickly as possible. And we gave them a little bit of training about that. We told them that it was okay to answer before the other person, before the recording finished the question. And, you know, we did these things to try and encourage them to respond as quickly as possible. We ran this experiment completely over Zoom because it was right in the middle of the pandemic. And we used the Zoom recording function to create an audio file of the testing session. We threw out the video file because we didn't care about that. And in the local condition, we took this slideshow that we prepared and we emailed it to the participant, and they downloaded and played it on their own computer. And for the remote condition, the experimenter played the slideshow on their computer using the share screen function. And that's how the participant viewed it it was transmitted via Zoom. Now, our primary prediction was that the interval between the offset of the question and the onset of the response, which is sort of the analog of turn transition time, that would be shorter in the local condition when they played it locally from their computer versus in the remote condition, because of the variable electronic transmission delays in the remote condition that were likely to disrupt the proposed neural oscillator. Now, we needed to control for all factors other than local versus remote. So half of our participants did the remote block first, the other half did the local block first. And the same questions were used in the local and remote blocks for different participants. So that was counterbalanced too. One other variable in the experiment was the predictability of the sentence. And this is important because it's related to how early they might be able to plan their response. So the question on the screen, the first question on your screen, is red your favorite color, is an example of one of our predictable sentences. Because if you hear is red your favorite, already you can imagine that that's going to end asking about your favorite color. You can plan your response before the sentence ends. Other stimulus items, you couldn't, had an unpredictable word at the end of the sentence, and so you couldn't begin planning your response as early. And these predictable and unpredictable sentences were pre-normed by on another research project prior to this study. So here are the results from our Q&A experiments. And the thing that should jump out at you is that the gray bars are a lot shorter than the white bars. And that's because the gray bars are our local condition, the white bars are the remote condition. The white bars are about 500 milliseconds longer than the gray bars. So this is a big effect of locality. Or if we interpret it a little bit more, we'd say like the Zoom delay was about 500 milliseconds, the delay in response time related to hearing it over Zoom. Another thing to notice here is that even though it's a fairly artificial task, we were successful in getting people to respond pretty quickly in the remote condition. So if we look at the predictable local conditions, sorry, I think I might have said that wrong before. If we look at these two gray bars, which are predictable questions in the local condition, we see that the response times are about 225, 250 milliseconds, which is pretty close to average response times. They're somewhat slower in the unpredictable conditions, and we saw that same predictability that was expected, and we saw that same predictability effect in the white bars as well. So there was an effect of predictability, which was sort of a manipulation check, I guess, to make sure that people were planning their responses as quickly as possible. Okay, so the great thing about this experiment was the control we had over all of the stimuli and the control over the length of the responses. The thing that was not so great about it is it's not very much like conversation. And so we wanted to look at actual natural conversation in our next experiment. And this was still during the pandemic, but I had 3 undergraduate experimenters that each were able to find 4 people within their pandemic bubble with whom they interacted without masks. And so we had each experimenter carried out a conversation with each of their 4 friends, the 4 friends that were participating in the study. One conversation face-to-face and another conversation remotely over Zoom. They alternated whether they did the face-to-face first or the Zoom first. We also had two topics that they talked about. One was pop culture and the other one was life in Ann Arbor. And they also rotated that across first block, first conversation, second conversation, and whether it was in the conversation carried out over Zoom or carried out face-to-face. So if you take a look at the spectrogram here, you'll see that there's a lot of variability in the length of the responses and the types of things people say and the amount of disfluencies in the responses. And there's also commonly overlap between speakers. So this, the audio data from this experiment had a very different feel from the audio data in the first experiment. And this really felt like normal conversation. So we again found that transition times were much longer in the remote condition compared with the local condition. We also found that people took longer turns in the remote condition and therefore switched speakers less often, which might have been a strategy that they adopted for managing the heavier cognitive load when conversing over Zoom. You'll notice that in addition to the local versus remote effect, which is the darker gray bars compared to the lighter gray bars, there's also an effect where the experimenter has longer transition times than the participant. And that's because our experimenter was responsible for keeping the conversation going for at least 8 minutes so that we would have enough data from each conversation. And so if there were a kind of longer pause in the conversation, it would be the experimenter who would break that pause to keep the conversation going. So of the 3 different paradigms we've used, this one is the most natural. And you can see that, especially for the participant, transition times are quite fast. So in the local condition, they were averaged under 100 milliseconds, and they were around 250 milliseconds in the remote condition, which is not bad at all. I mean, it's fairly typical. Okay, one thing about this experiment that we didn't love is that the experimenter was such a big part of the conversation. So for our next experiment, we were able to get back into the lab and bring people in person to participate in our study. And we wanted to study 2 participants conversing with each other. But we needed to make sure we got enough data. So we needed to sort of, without intervention from the experimenter, to keep the conversation going with lots of transitions between speakers. And so we decided to use this map task, which other researchers have used for kind of other purposes, but we thought it would work well for this situation. So the way the map task works is that each participant gets one of a pair of maps. And the maps have some of the same landmarks, like they both have this pyramid, and then they have some different landmarks, like the A map has a telescope and the B map has a country road. And the goal was, through cooperating with one another, but not looking at each other's maps, you have to annotate your map so that it contains all of the landmarks that are missing but are on your partner's map. So each map has 5 landmarks that are on both maps and 5 landmarks that are unique to that map. So at the end, everybody should have 15 of the same landmarks in the same place. And everybody was able to complete this task successfully. We ran, everybody who came in did 2 different pairs of maps. The first set they did, well, I shouldn't say first, they did one set face-to-face and one set in different rooms over Zoom. The face-to-face one they sat across the table from each other in our lab, and they had a manila folder that they put in front of their map so that the other participant couldn't see the map. And we varied whether they did the face-to-face first or the Zoom first. For both the face-to-face and the Zoom, they were masked because that's what we were doing on campus at that point in time. And when they were in the Zoom rooms, they kept their video on. the whole time. So, so this task turned out to be great in terms of getting enough turn transitions, taking about the right amount of time, and to give us the right amount of data. But a major difference between this paradigm and the previous ones is that people had something to do on the maps. They were annotating the maps, they were writing out words. Many of our participants actually drew in the pictures also. So they weren't just writing words, but they were drawing the picture. And also there was a strategizing component to it that was missing from the other conversations. And what this meant is that there was a lot more variability in transition times because we had some very long pauses, more than 6 seconds in both the local and the remote condition, where people were either writing or they were thinking about what to do next and how to perform this task. So despite the noisier data, so in a minute, I'll show you this slide with the previous data slides so that you can compare, but I'll tell you that the error bars on this slide are much bigger than the error bars on the other slides, even though we have more data. So in the conversation experiment, there were just 12 participants. Here we've got 30 participants, but because of the nature of the task, it was much more variable. But despite the additional variability, the Zoom delay effect was robust enough that we still got it. So we replicated it again here with this study where the experimenter was no longer part of the conversation. So we can look at all 3 studies together, and the size of the effect differs somewhat from study to study, but there was a lot of consistency across the 3 experimental paradigms, even though the paradigms were quite different. And so we're confident that the Zoom delay in turn transition times is real. And such a Zoom delay is predicted by our hypothesis that an automatic neural oscillator tracks the speech rate of our conversational partner and helps us time the onset of our responses. And we think this is one part of what some people have called Zoom fatigue. So it's kind of died down now, but for a while you saw a lot written about Zoom fatigue in the popular press. And I think it's important to keep in mind that our oscillatory explanation is probably just one part of the reason why people report Zoom fatigue. So other things that have been suggested have more to do with the video aspect of Zoom. For example, self-monitoring of yourself, because there's this image of you acting out the conversation as you're carrying it out. Another issue is eye contact. So the face of the person you're talking to is right there in front of you, but you can't really establish eye contact with them. Some of the body language may not be visible depending on how far the person is from their camera. So there are various things that together probably lead to what's been called Zoom fatigue. And interestingly, people, to my knowledge, people don't complain about conversing over cell phones in the same way. This may be because, in part because cell phone calls tend to be shorter than Zoom calls. Usually if you plan a Zoom call, it lasts sometimes 30 minutes or maybe even an hour. Or maybe because the visual components of Zoom fatigue are especially salient. But we think that actually most types of electronically mediated conversation should have this Zoom delay in transition times because of the inevitable variable electronic transmission delay. So we were curious to know whether or not we would find longer transition times suggesting disruption of that automatic oscillator in cell phone calls. And this is your bonus experiment. So we basically did the same map task again, and the local condition was exactly the same, but for the remote condition, we sent them into the rooms with their cell phones. And we didn't do a regular cell phone call because we needed an easy way to make a recording of it. So what we did was we had them dial into a Zoom call, and the Zoom connected the call and made the recording of the call, but there was no visual, it was audio only. And people reported that the remote condition felt just like a regular cell phone call. And as you can see, there is a very robust Zoom delay in the remote condition. It looks quite a bit like what we saw. This is the graph from the previous study using the map task with Zoom. And if anything, over the cell phone, the effect is even bigger. So wrapping up, across a range of paradigms, we found that transition times between speakers are consistently longer when the conversation is mediated electronically, such as over Zoom. This is predicted if an automatic oscillator is getting disrupted by the variable electronic transmission times over Zoom. If we normally use this automatic oscillator in face-to-face conversations, but we can't use it over Zoom, it means there's more effort required to time your responses because you have to, if you can't rely on this automatic mechanism, you have to rely more on other cognitive mechanisms, and this could contribute to Zoom fatigue. But this problem seems to apply to other forms of electronic transmission, such as cell phone conversations as well. So one of the things that people think about when they think about Zoom fatigue may be a lot of it related to the visual processing weirdnesses of Zoom. All right, so before I just thank you for listening, I want to acknowledge my undergraduate researchers. So Miles Williamson, Pedro Fonseca, and Alana Mermelstein helped me design and carry out the first two experiments. And Miles and Pedro have continued to be involved, as well as Xiao Du and Elizabeth Atchett in the last two studies, the map task studies that I was talking about. And I couldn't do this work without their help. So thank you to them, and thank you to you. And I'd be happy to take any questions.
That was great. Thank you. Thank you so much, Julie. That was a lot of fun to hear. And I just first have a couple things, a couple comments, and then I have a few questions for you. So first of all, I just want to say that it's incredibly impressive that you're able to get all this done during COVID. And I mean, this, I would imagine, is just a lot of new technology and research that you had to figure out, partly while everyone was in lockdown. So that's really great and very creative that you're able to collect this new data during this really tough time. The second thing my second comment is that I think when we were discussing the idea of you doing this, I think you pointed out the irony of doing this, talking about the problems with Zoom, talking about challenges with conversations while we are having a conversation on Zoom. I just wanted to highlight that, but I don't know if it's an irony, but maybe it's we can illustrate the challenges, illustrate your findings here. And the one, just as a PSA, maybe everyone knows this, but I do find it annoying seeing myself on all the time. I think that's probably part of Zoom fatigue. And I very late in the day found out that you can actually turn the self view off. I find the meetings much more bearable that way.
Yeah, it's a great tip.
Yeah, so great. So I just had a few questions for you. I want to go back to the beginning, like the pre-Zoom studies. And I thought that was really interesting way of formulating this that I never really thought about before. That, yeah, of course, there's not a pause where someone thinks before responding. And so, yeah, you're formulating your answer while you're formulating a response while the other person is talking. I was just wondering if work has been done by you or anyone looking at individual differences and how quickly people respond. I can imagine that might map onto certain personality traits, like being very quick to respond because they're really not listening to what the other person's saying, for example. I was wondering if there's any data on that at all that you might know of.
That's a great question. We actually tried to look at that. So we measured individual differences in personality using a Big 5 personality test. And then we also measured individual differences on various aspects of cognitive control. And we tried to see if that was correlated to mean transition time. And we didn't actually get anywhere with that, but I tell you, it's very painstaking to take this audio data and transcribe and segment it all. It takes a really long time. And for individual difference studies, you need lots and lots of participants. So we may just never have sort of gathered enough data to make a go of it. Let me pivot in a different direction though. Yeah. One thing that makes a huge difference is the type of response you're producing. So if you are just kind of agreeing or disagreeing with a short response, those tend to have very short transition times. Whereas if you're answering a question, particularly an open-ended question that might require a memory retrieval, and maybe you can't really answer it till you hear the whole question, then we see much longer transition times. So that's maybe the most powerful predictor of transition time I've found is sort of what the functional type of response you're making.
Gotcha. Okay, great. Thanks. And my second question has to do with your experimental work with Zoom. And so I just want to get a clarification. So it seemed like, if I understood, most of the studies were like in person or Zoom, but I wasn't sure if that was the case on the first experiment. Was it?
Yeah, the question and answer study. So yeah, we had to sort of rig a local condition because people were not local. They weren't coming into the lab. They were in their own dorm rooms or houses or wherever they were. So we created this slideshow and we sent it to them, we emailed it to them, and then they played that locally on their computer in the local condition.
Oh, right. Okay.
So it wasn't face to face, but it was a local condition because they were the questions weren't being transmitted electronically over the internet. They were just being played locally.
Mm-hmm. Okay. I understand that now. Thank you. Well, I was just trying to think of a way if you could have this blinded. The experimenters wouldn't know if they were on Zoom or not, but based on the end, like this even happens with phone calls and everything. It's like there's what you want, the comparison has to be in person, right? And that can't be blinded, right? Everyone's going to know, right? There's no way, it's not something specific to Zoom. It's just.
Yeah, you mean blinded to the participants.
Yeah, like they wouldn't know if it's if it's Zoom or some kind of higher quality, faster interaction. But it seems like it's having it through the medium. Any kind of like video is a problem, right? Or audio.
Yeah, I mean, through the electronic transmission. But what I would like to do is be able to control the transmission lag in the electronic transmission. And I'm sure that if I hook up with the right engineers, there's a way to rig this so that you can effectively have a transmission lag of 0, or you could have a transmission lag of, say, 100 milliseconds or 200 milliseconds, and you could either have that transmission lag be constant or you could have it be variable. And I'm guessing that it would be easier for us to adapt to a constant transmission lag than a variable one. A lot of the problem is the variability and not so much lag. But yeah, I would love to do that. And I don't have the technological expertise unless I can find a good collaborator to help me do it.
Right. Yeah, that's really interesting. I think that's a great idea. Yeah, and that brings me to the next question, was about, like, if I imagine this would be something like that you haven't been able to analyze yet, but I was just wondering if there's any effect of, and if you guys looked into internet speed or computer speed. I mean, I imagine sometimes it's just horrible and the buffering is so extreme, but if that's like, if that was looked at, or if maybe the participants were in a dorm at the University of Michigan, so it may have been more uniform.
Yeah, so Zoom has a user tool that allows you to look at the lag dynamically throughout the conversation.
Oh.
And so we tried to do that. It was difficult to like record it because it would change, you know, it was a dynamic lag. And so it was changing all the time. And there wasn't any way using just their tools that we could, you know, come up with an average lag for a conversation. But then it gets worse than that, because that lag turned out only to be like a part of it, a part of the problem. What they were reporting would be on the order of like 30 to 60 milliseconds of lag. But then if you just make an audio recording of, you know, Zoom, but you're kind of in the same room, but you're talking over Zoom, you can tell that the lag is really more like, you know, 200 milliseconds or something like that.
Yeah.
So it's really challenging to get an accurate estimate of the lag. And because it's dynamic and varying, what we really need is to be able to control it, you know, like to rig something up where we know what the lag is.
Yeah. Okay. Great. And yeah, so, and my last question is just more practical. If you have any thoughts of how we can, it seems like some of this is just built into the medium, but if there are any thoughts on how we can compensate or reduce Zoom fatigue going forward. You mentioned a lot of the issues, and other than taking breaks, I don't know if you have thoughts of what can be done. It just seems, regardless, going forward, this will be part of our lives.
Yeah, I agree. And I mean, I have to be careful because we've only looked at two-party conversation, and a lot of the Zoom experience that people have is meetings or maybe small groups, and there may be different issues with those situations than one-on-one conversations. But I think to the extent that video is a problem, you're right, it's easy to control that. Just turn off your own the thing that's mirroring yourself back to you.
Yeah.
But I think we can't get away from the Zoom delay that I was researching. But on the other hand, I'm not sure that that's bugging people the same way that this other stuff is. You know, it may be subtle enough that it's not really bothering anyone. It bothers me, and I noticed it over cell phones too, which is one reason why I wanted to do the cell phone study, because I find I'm always like stumbling over the other speaker and you know, coming in at the wrong time on cell phones. Also, I noticed it both places. But I think, you know, one of my research assistants said, but you know, cell phone calls are shorter and they're spontaneous and it feels less like work. You know, all of these are things that make the electronic lag easier to deal with on cell phones than Zoom.
Yeah.
But I don't have any great solutions, but a lot of compassion for the fatigue.
Okay, well, great. Well, thank you so much, Julie. That was wonderful. It's been a lot of fun. Appreciate it. All right.
Okay, thank you. It's been fun.